Whenever we have a problem with arbitrary n, it's a little bit difficult to see what the pattern is without doing an example. So I think it's good to try out a simple example, or at least somewhat simpler, by computing the determinant of the same matrix, but where n equals, let's say, 3. So we have a 3 by 3, and we want to compute this determinant. And we want to compute it in such a way so that we can use some of the ideas for computing this determinant and abstract it to that more general case. Now, this isn't the most simplest way to do such a thing, but it's one way, and I'm sure there are many, many other ways to compute this determinant, some of which may be certainly more clever than the approach that we'll take. So we're going to do this by essentially row reduction. And for the first step, we're going to get rid of the ones underneath the top left one, and by just subtracting the first row from those. So if we do that, that doesn't change the determinant, and we get the top row is left alone, and then the rows below it look like 0, 0, lambda 2 minus 1, lambda 3 minus 1, and this becomes lambda 3 cubed minus lambda 1 cubed, squared, and lambda 2 squared minus lambda 1 squared. Now, when we lambda 2 minus lambda 1 is actually a common factor in this second row, because this becomes lambda 2 plus lambda 1 when we pull that out, and this is lambda 3 plus lambda 1. So when we distribute out, we get lambda 2 minus lambda 1, lambda 3 minus lambda 1, times the determinant of what's left over, which is 1, lambda 1 squared, 0, 1, 0, 1, lambda 1 plus lambda 2, lambda 1 plus lambda 3. And this happened because the determinant, remember, when you take the determinant and you multiply any row or any column by a number, you can distribute out that one number for that one column in this determinant. You can think of the volume. If you scale one side of the room by a factor and another side of the room by a different factor, then the determinant is computing the area, and you scale by both of those. But for each side, you only distribute one of them. So now we're looking at this, and we want to compute the determinant of this. Now, of course, what's left over is a 2 by 2, so it's very easy to compute the determinant. But if we wanted to have an inductive proof, if we did a similar calculation here for a larger matrix, what we would have is lambda 1 through lambda 1 to the n minus first power up here, and then we'd have a much larger matrix, which isn't very easy to compute the determinant of by some explicit formula. It's sort of complicated to write. So what we want to do is we want to think of how to compute this maybe more conceptually. And what we can do is, notice that lambda 1 appears here in each of these two terms. And if we multiply the second column by lambda 1 and subtract, what happens is this cancels, the lambda 1 cancels, the lambda 1 cancels, and you're only left with lambda 2 and lambda 3. And you also don't change the determinant because you're taking one column and adding it to another. So this is also equal to the determinant of what's left over after you do that subtraction. This is 0, 0, 1, 0, 1, and then just lambda 2 and lambda 3 left over. Well, you can even do something even a little bit more simpler now. Now you have a 1 here. You can multiply this by lambda 1 to get rid of that. So I'm not even going to write that whole step out. We can just erase this and put a 0 here. And now, here's the amazing part. What's left over after you perform these operations is another Vandermonde matrix on the bottom right corner. And we can continue this process now, because the determinant of this, because this is a 1, is equal to the determinant of this. So we've reduced our problem from an n by n matrix to an n minus 1 by n minus 1 matrix of the same form. And if we keep going down further, up until maybe this step, or even further than that, then we would find out what the determinant of this matrix is. So if we did that procedure again, of course you can compute the determinant of a 2 by 2, no problem. But if you did that procedure again, subtract, you get a 0 here, move that over, you end up getting lambda 2 minus lambda 3. It's already of that, it already breaks up like that pretty easily. And you get lambda 2 minus lambda 3, that pops out. So what you end up getting is the product of I and j. Let's say I is less than j, and j is less than or equal to 3, and I is greater than or equal to 1, of lambda j minus lambda I. So you actually get the product of the differences of all of these different eigenvalues. And because we're assuming that the eigenvalues are distinct, all of these numbers are not 0. Therefore, this is not equal to 0. And so we automatically know that the determinant of this matrix is non-zero. So we can make a guess that the determinant of that more general matrix, of that more general Vandermonde matrix, is exactly the product of the differences of all of the eigenvalues. And therefore is not 0 if they're distinct. And we can prove this by induction. We already know what happens when n equals 1, or when n equals 2, and even n equals 3. And so what we can do is, if we assume that this formula is true for n, and go to n plus 1, then what we want to do is reduce that problem to this one and show that those numbers factor out, and then we can apply our induction hypothesis and prove that this formula holds more generally. And the way we do that is very similar to this. So I'll put a question mark here, and I'll write what this equals. By doing this first step, which was here, this first step in subtracting the first row from all of the rows below it, what we end up getting is the determinant of, and here we have a bunch of zeros below the ones. So we have 1, and I'll write 2 rows just so we see more of the pattern. This is a 0, 0, lambda 1, and then this is lambda 2 minus lambda 1, and this is all the way down to lambda n minus lambda 1, all the way up to, and let me write 2 additional terms here. So this is going to be lambda n minus 2, lambda 1, n minus 1. Now, this is lambda 2 to the n minus 2th power minus lambda 1 to the n minus 2th power. And here we have lambda n minus 1 minus, 2 minus 1. That's a 1. Okay. Now, at this point, we can follow a similar procedure by pulling out a lambda 2 minus lambda 1 from each of the terms, but then we would have to figure out what is lambda 2 to some power minus lambda 1 to that same power divided by lambda 2 minus lambda 1? We could do that and factor it out by using polynomial division, find out what the corresponding factors are, but maybe that's not the best way to do it. Another option, although that method, of course, teaches you a lot about how to do polynomial division in case you haven't seen it before, it's quite nice. But maybe there's another easier way, similar to what we did over here. And what we did here was we took the second last column and we multiplied it by lambda 1, and we took the difference here. We could have also done that in this step. It just might have been it might have looked a little bit more complicated because of the higher powers. But let's try to do that anyway. If we multiply the second last column by lambda 1 from the last column, the power here will be n minus 1, which will match this one. And these two terms will cancel, and you'll just get 0. What happens to this term? If you multiply this by lambda 1, so let's write this out. So we have lambda 2 n minus 1 minus lambda 1 to the n minus 1 minus, multiply this whole term by lambda 1. That becomes a plus lambda 1 to the n minus 1, and then what's left over is minus lambda 1, lambda 2 to the n minus 2. These two terms conveniently cancel, and what you're left over with is lambda 2 appears, the highest common factor is lambda 2 to the n minus 2, so we can pull that out. And what's left over after we pull that out is lambda 2 minus lambda 1. And therefore, we can much more easily see that this factors out after we do this subtraction. Now, imagine we've done that for this last column here. Now we have this second last column, which still has all of these complicated terms. But what does this term before it look like? Lambda 1 to the n minus 3, and then it's lambda 2 to the n minus 3 minus lambda 1 to the n minus 3. So you can just see it's of the form n minus j. And if we multiply this by lambda 1 and subtract it, well, these two terms will cancel, and a similar thing will happen here. It's just that the power will now be not lambda 2 to the n minus 2, but lambda 2 to the n minus 3 after we take this difference. And so if we keep going in this direction, taking all of those successive differences, we will be left over with, so this determinant equals the product of lambda j minus lambda 1, and j goes from 2 to n, and we're left over with the determinant of a smaller Vandermonde matrix, which looks like 1, 0, 0, and this term is 1, and it's all the way, 1's all the way down. Let me write just the first and last ones. We also have zeros here, up to the last term. Now, what is this term here? It's lambda 2 to the n minus 2 now, all the way down to lambda n to the n minus 2. And if we assume the induction hypothesis, then we know that the determinant here is the product of lambda, let me use a different letter, k and l, so k minus l, where k is strictly greater than l, and l runs from this time 2 to n, and k. So we end up getting, after all of this work, by using that induction hypothesis, we get that this is this expression right here. And in particular, this says that our determinant is non-zero. So we can compute the inverse of this matrix if we wanted to.